Thank you for inviting me. This work is somewhat like a little bit older work of mine, but it's very close to my heart, and I know that recently you've had talks on scientific progress, so I wanted to get your opinion on these things, and I wanted to try it out on this audience. So Popper's notion of truth-likeness, or sometimes verisimilitude, was famously trivialized independently by two guys in the 70s, Pavel Tichy and David Miller. And the problem is that for any two false theories on his notion, neither is more truth-like than the other, so that doesn't do much good for a theory of truth-likeness. And it was just one of these classic nuisances that you get in when you play around naively with propositional logic. Oh no, not this one. Now, more and more sophisticated notions of truth-likeness were proposed, and this project is ongoing. I think it makes takes on for my taste, a height of sophistication in Nilaudo's work. So in some ways, the metaphysical problems with the definition have been solved, but the epistemic and methodological ones have not. And Nilaudo makes a kind of disarming admission about this. He says that the problem of estimating verisimilitude is neither more nor less difficult than the traditional problem of induction. So although the definition works okay, the problem of inferring which of two theories is more verisimilar is reduced to the hardest problem, right? So it doesn't feel like we've made a lot of progress on progress. Now, Lakatos picks up on this as well. He says, from the statement that the verisimilitude of our scientific theories can increase, it only follows that our knowledge can grow, but without our knowing it. If so, even Popper's newly found fallibilism is nothing more than skepticism together with a eulogy of the game of science. Popper's theory remains a metaphysical logical theory which has nothing to do with epistemology. Ouch. Ouch. You can find this sentiment echoed in a recent book by Larver, a more recent book by Larver, but I won't read it out to you. I think the maneuver that I want to make that will allow us to kind of move beyond these problems is what I like to call the virtue ethical maneuver. So when virtue ethicists about knowledge feeling themselves in a bit of a dead end with the justified true belief model of epistemology, this kind of maneuver where they say, since justifiedness is a property of a belief, it's very difficult to adjudicate disputes if the belief is treated as the bottom level object of evaluation. Instead, we focus on the deeper concept of an intellectual virtue and treat the justifiability of belief as derivative. So here they go up the type from beliefs themselves and trying to justify those to up the type to a character or a belief forming disposition, and try to justify belief forming disposition, which gives you a lot more structure to work with. And so similarly, I want to go up from the type theories to methods, which are dispositions to infer theories on the basis of observation. So what we want to justify is rather than trying to say that any particular sequence of theories, and this is now kind of a spoiler, any particular sequence of theories is increasing in truth-likeness, we want to say that our method has a disposition to make progress. So here's a first idea, a first and very naive idea. Say that a method for answering a scientific question is progressive, if and only if the chance that it outputs the true answer of the answers that are on the table, we think of a question as just a set of answers, the chance that it outputs the true answer is strictly increasing with sample size. Now, that notion makes sense, even if it doesn't make sense to ask which of two false theories is closer to the truth, so long as one of the answers is true. You don't need a notion of verisimilitude. But you can actually employ the existing metaphysical notions of verisimilitude here, because instead of it's a kind of parametric idea. Now you can say, well, if none of the answers are true, the idea should be that the method is progressive if the chance that it outputs the most truth-like answer is strictly increasing with sample size. And now you can use the theory of truth-likeness that was developed by people like Nino and plug it in here. Or if you don't like any of those things and you're more of an instrumentalist, you can say, well, the most useful answer. I think nothing that I say here really depends on too much on that. But that is too high a standard, so we have to back off a little bit. Demanding that the chance of outputting the right answer is strictly increasing with sample size is impossible. But we take it as a kind of regulative ideal, and we seek to approximate it. So we say a method for answering a scientific question is alpha progressive if and only if the chance that it outputs the true answer never drops by more than alpha. So here, this is a stylistic kind of picture that's trying to show you plot the probability of outputting the true answer, whatever it is, against the sample size. And we see that this method is more progressive because if you pick any two sample sizes, it will never drop by more than a little bit at the higher sample size. And here, there's all sorts of precipitous drops in the chance of outputting the right answer. And what does that look like? Surprisingly, many statistical methods, like standard statistical tests, are not even approximately progressive. So here, I've picked a particular parameter, and I'm testing some hypothesis, and the hypothesis is false, and I'm plotting the probability of correctly rejecting the hypothesis as sample sizes increase. And what you see is this sawtooth behavior of the test, where there are certain unlucky sample sizes, like between, I don't know, whatever this is, 35 and 39, where actually the probability of correctly rejecting drops by a significant amount. So this is a kind of perverse situation where more data is bad. And there are certain lucky sample sizes and certain unlucky sample sizes. And if your method has this disposition, if the sizes of the teeth on the saw are rather large, what that means is that it has a built-in disposition built in to fail to replicate correct results. So you can also think about this as like it's building in a tendency for replication failure, but not failing to replicate false things, which is good, but rather failing to replicate true things, which is bad. I mean, so imagine like you go to a funding agency, you did your test of a drug at some sample size of 1,000, and you go to the funding agency and ask to do a replication study at a larger sample size. And when you do the power analysis, you say, actually, the probability of correctly rejecting is now lower, even though we're going to spend more money and potentially expose more people to side effects. Not only is that epistemically perverse, it's also, I mean, unethical, presumably. So yeah, you shouldn't do it. Now, the good news is that now this is like a preview for a theorem that you can't fully understand because I don't have given you the definitions, but this is just a teaser. If the answers to a question can be enumerated in agreement with simplicity, and you don't know what that is yet, because I haven't told you, then it is progressively solvable, which means that it's alpha progressively solvable for every alpha, which that means that you can take your tolerance for wiggles as you converge, as the probability of convergence, the probability of outputting the right answer converges to 1, and you can bound them arbitrarily small, so long as you can enumerate them in agreement with simplicity. That's the good news. So you can make those wiggles arbitrarily small, although you can never eliminate them entirely. So that's nice. Another nice thing is that every alpha progressive solution to a question must satisfy a version of Occam's razor, what I call Occam's alpha razor. And what that is, to me, is a non-circular epistemic justification of Occam's razor in statistical science. What do I mean by these things? I mean non-circular because I haven't assumed that the truth is simple or anything like that. I haven't put down a prior over possibilities or introduced a, some Turing machine or whatever, or some preferred language or anything like that. It's just that a systematic preference for simple hypotheses is a necessary condition for a kind of virtuous convergence to the truth, a nice, smooth convergence to the truth without a lot of precipitous drops in the probability of outputting the right answer. And for my taste, this is not just a non-circular justification, but it's also an epistemic justification. Well, why? Because some people say, well, this is a generalization of an idea. Well, it's inspired by an idea of my advisor about keeping the number of mind changes on the way to convergence to a minimum. And I think the objection to that was frequently, well, minimizing the number of mind changes on the way to convergence, well, that's a merely pragmatic thing. That's not an epistemic thing. But for my taste, this is perfectly epistemic. I mean, if you want to avoid avoidable non-monotonicities on the way to convergence, or if you have an idea of a virtuous convergence, a virtuous way of converging to the truth, a virtuous way of seeking truth without unnecessary detours and bold faces, that kind of thing, then to me that's an epistemic justification, not a merely pragmatic justification. Now, I think, right, so what does that mean? That means violating Occam's razor, and I haven't yet told you what I mean by Occam's razor, but it means designing in a tendency to fail to replicate true results, and that's bad. If you have classical taste, you can think of Plato's stability criterion for knowledge, and basically obeying Occam's razor is a necessary condition for the truth to be a fixed point of inquiry. And another nice thing is that a carefully calibrated Popperian methodology of conjectures and refutations can ensure that the degree of backsliding is arbitrarily low. So there is something we can say about a carefully calibrated regime of conjectures and refutations. It has a certain virtue. It means it will, if it's guided by simplicity, which that was Popper's idea anyway, which means it will have this nice convergence property. Okay, I want to make some philosophical points before I move on to delivering the promised definitions, right? Traditionally, the way that people understood epistemic justifications for theoretical virtues was synchronicity. So here, if you read the Stanford Encyclopedia article on simplicity, they will say something like this. Well, rather, they will say literally this: justifying an epistemic principle requires answering an epistemic question. Why are simpler theories more likely to be true? Now, okay, I mean, I think if that's what you mean by an epistemic justification, then you shouldn't believe anyone that they have an epistemic justification for your Occam's razor. I don't think anyone can prove to you in a non-circular way that simpler theories are more likely to be true. I mean, what would you really mean? What would you mean by likely? Well, you're just imposing some prior and then discovering that, oh, all along I believe that theories are true, but you're just doing psychology, not epistemology. And demanding synchronic justification leads to a kind of despairing attitude about justifying the theoretical virtues. So here is Larry Loudon in 2004. No one has shown that any of these rules is more likely to pick out true theories than false ones. And these rules included things like Occam's razor, parsimony, preference for parsimony, or unifiedness. And it follows that none of these rules is epistemic in character. Well, I mean, no one has shown, therefore it doesn't, it doesn't really follow, but you see why that kind of synchronic attitude, when you set the bar very high, it leads you into this kind of despair about justifying the theoretical virtue. Going diachronic allows us to demonstrate that a systematic preference for simple theories is a necessary condition for a diachronic notion of progress. And that, for my taste anyway, is no less epistemic than this synchronic notion. That's just, infeasible. Okay, so to flesh things out a little bit. Can I close this thing? Do I dare? No, I can't get there. You can't get there from here. No. Okay. So right. So this is the problem context. I have a set of models, W, a set of models, in this case, a set of contextually relevant epistemic possibilities. Each of these models determines a probability distribution over the data that you might see. Now we partition the question into a countable set of answers. I didn't draw it to be countable, I draw it to be finite, but it doesn't matter. So fancy Q is the set of answers. And fancy Q sub M is just the cell containing M. So it's the answer true in M. Now, we say a method is a statistical solution. What is a method? It's a collection of functions from data to conjectures, one for every sample size. That's why it's Ln, one for every sample size. And we say it's a solution to a question if whatever model is generating the data, the probability in that model that the method eventually conjectures the true one converges to 1 as sample sizes increase. It's ordinary statistical consistency. And we say that a question is solvable if it has a solution. We have some nice topological characterizations of which questions are solvable, but that's not the topic of today. Now, a solution to a question is strictly progressive if whatever model is generating the data, and for any two sample sizes, n1 smaller than n2, the probability of outputting the right answer at n2 is strictly larger than the probability at n1. That's just saying that the probability of outputting the right answer is strictly increasing with samples. Okay, like I said, we have to back off a little bit and introduce a fudge factor. So we say that a solution is alpha progressive if for any model that's generating the data and for any n1 smaller than n2, the probability that you output the right answer at the larger sample size is bigger if you give me a little fudge factor of alpha. And we say that a problem is progressively solvable if it has an alpha progressive solution for all alpha. So you can make that the alpha arbitrarily small. Now, I owe you a notion of simplicity. But before I can give you a notion of simplicity, I have to give you a notion of refutability, because recall Popper's notion of simplicity, which inspired ours, is about what is more refutable than what. So the rough version is that one hypothesis is simpler than another if it's more refutable, right? So which are the refutable hypotheses? Statistically refutable. I mean, famously in statistics, nothing is ever refuted by the data because everything just occurs with some probability, something occurs with small probability. So you have this, like, a lot of hair pulling about what is statistical refutability. So I'm going to give you a definition inspired by classically refutable hypotheses from the theory of computation, but not exactly that, obviously. So we say that a hypothesis, which is just a subset of, it's just a set of models, is alpha refutable if there exists a consistent hypothesis test of H with significance level alpha at every sample size. I'm going to give you more and more Baroque definitions of refutability because I'm then going to show you that they're all equivalent in the sense that they all lead to the same set of hypotheses. So they the same set of refutable hypotheses, whichever way you understand refutability. And you say that a hypothesis H is refutable to core if it's alpha refutable for every alpha. Now, once again, with symbols, we say that a hypothesis is alpha refutable if there is a sequence of tests such that if the hypothesis is false, the probability that the test rejects converges to 1 as sample sizes get large. And if it's true, the probability that you falsely reject is bounded by alpha at every sample size. So recall, like a classic example of a refutable hypothesis is, the sun will always rise, or all ravens are black. And if that kind of thing is false, you eventually see data refuting it, and so you can say it's false. And if it's true, then you just say, I don't know. So this is just like that, except the probability that you correctly say I don't know, or that you don't make a mistake, is rather than being 0. The probability that you make a mistake rather than being 0 is just small. The only difference. Now we can come up with more and more stringent notions of refutability. Like you might want, okay, I want that the probability of rejecting correctly, if it's false, converges to 1. I want the probability of falsely rejecting to be bounded at every sample size, but I also want it to converge monotonically to 0. Like it's better if the bound on falsely rejecting goes down. Bayesians often insist on that kind of thing. And it would be better if the probability of rejecting correctly, if it's false, is increasing monotonically. Unfortunately, you can't have that, but you can have like almost monotonically up. And so say that it's alpha monotonically falsifiable if you can send the alpha down to 0 monotonically, and the power increases almost monotonically, or rather the probability of rejecting correctly in every parameter increases almost monotonically. You can also come up with almost sure versions of this thing. These are all in-chance versions, but you can also come up with almost sure versions of this kind of thing. The good news is that according to a theorem by me, the monotonically statistically refutable hypotheses are exactly the closed sets in the weak topology on probability measures. So if that means something to you, it should be like, well, cool. If it doesn't mean anything to you, like whatever. But the thing to notice is that statistical refutability is a robust concept because there are many ways of defining it. And they all lead to the same set of hypotheses being statistically refutable. So even though we, generally speaking, I think the problem of deciding when a statistical hypothesis has been refuted is essentially unsolvable. It's a kind of conventional. It has a conventional aspect, like Popper agreed. It's essentially a methodological decision that you make socially as a group of people in a discipline or something like that. But there's much more structure in the question, when is a hypothesis refutable? And that's a much less arbitrary question than it seems for this kind of reason, because many different definitions give you the same set of refutable hypotheses. And if you want to read more about that, see this paper by me. Okay, now you sort of know what statistical refutability is, and I owe you a definition of simplicity. Right, so this is, there are many, this was my copy of The Logic of Scientific Discovery, which I love very much, which is presumably somewhere in Father's Space in Brooklyn. It had this cool cover, and there are many definitions of simplicity that you can find in there. And one of them is the subset definition. For two sets of models A and B, say that A is as simple as B if all refutable consequences of B are refutable consequences of A. Right? The annoying thing about this definition is that it confounds logical strength and simplicity, because if A entails B, then it's also simpler than B, which is annoying because we wanted, I mean, at least I wanted to capture relations of empirical underdetermination, not logical relationships, right? And the bad thing about this kind of definition is that it drives you to say very specific, to make very specific conjectures. And it also says that the worst epistemic sin you could do, and the biggest in the sense of the biggest violation of Occam's razor, is to suspend judgment. And if you suspend judgment, that's like the weakest proposition that you can say in this algebra. And that is like a huge violation of Occam's razor. And that's, in my opinion, philosophically wrong. Because suspending judgment is not a violation of Occam's razor. I mean, that's just the wrong kind of thing. So a simple fix is we just say, well, they have to be competing theories. Like if A and B are two competing disjoint sets of models, we say A is as simple as B if all refutable consequences of B are refutable consequences of A. And that solves a lot of problems. It solves the problem that you since nothing is disjoint from W, the set of all models, nothing is simpler than W. And in fact, so okay, nice. You're allowed to suspend judgment now. But there's another annoying problem, which is the tack-on problem, I think is what, or the tacking problem, maybe quite be more called the tacking problem. So if the set of strictly linear, the set of strictly linear hypotheses, let's say we're doing curve fitting, right? The set of strictly linear curves is simpler than the set of strictly quadratic ones. Meaning, like linear, you only have a non-zero coefficient on the linear term, and a quadratic is ones like you have a non-zero coefficient on the linear term, but also a quadratic term. Okay, linear is simpler than quadratic, great, because anything that falsifies one also falsifies the other. But if you tack on something like it's either linear or the cat is on the map, then that's no longer simpler than quadratic, and that's just kind of annoying. And you have to make some kind of decision, and the decision that we end up with is that, oh yeah, that doesn't do anything. We say, for any two disjoint sets of models, say that A is as simple as B, if and only if all refutable consequences of B are consistent with A. Another way of saying this is like, there is a way that A can be true such that B will never be refuted. All the information you'll ever see will be consistent with B, even though B is false. There's a way for A to be true such that all information you ever see is consistent with B, even though B is false. One of the nice consequences of this kind of definition, so instead of saying topologically, this is just the difference between A being a subset of the closure of B like the first one is A is a subset of the closure of B, and the other one is A meets the closure of B. And the nice thing about this definition is that every closed hypothesis is a simplest hypothesis. That also means that every refutable hypothesis is a simplest hypothesis. Nothing is simpler than it. However, this has the nice property of being transitive, and this does not. So it's kind of like, do you prefer order theoretic things, in which case you're going to go for something like this, or do you want? To me, this one is better because it means that so long as you conjecture a refutable hypothesis, you are saying something simplest, something than which nothing is simpler, and therefore, you know, blessed by Ockham. To me, even though that's less elegant, order theoretically, it's more correct philosophically. Now, okay, now you know what all the terms mean. If the answers to Q to the question can be enumerated in agreement with simplicity, then the problem is progressively solvable. So things like, is it strictly linear, quadratic, cubic, those you can enumerate in agreement with simplicity. Or if you're doing, if you're learning a causal DAG, you know, having strictly more, the same set of variables, but strictly more in the sense of subset, causal relations, that is also more complex. It captures many of our standard intuitions about what is more complicated than what. But when does it fail? When can you not? Enumerate the answers to a question in agreement with simplicity? Well, it's going to be something like, if I asked you, is the degree of the polynomial generating the data even or odd? Well, then even is simpler than odd, odd is simpler than even, and you're in on that. But it's a kind of perverse question. So it's kind of a norm of asking questions, I would say, that, well, I have two norms of asking questions. The two norms of asking questions I have is that these two definitions give you the same order over the answers, which is typically what will happen. And there are no circles. Because, you know, asking if like, you know, how many fundamental particles are there? That's like a normal scientific question, or like something like Kant asked, you know, how many times can you divide matter? Like, is there a limit? Like, or how many times can you split whatever this piece of chalk? But asking, can I do it an even or odd number of times, is a weird thing to ask. And nobody would do it. So, yeah. Most scientific questions have this. And so if this is an enumeration of the answers agreeing with simplicity, meaning you never put something simpler after something more complex, a progressive method can be constructed by just attempting to falsify larger initial segments. Like, first I attempted to falsify this, and this, and that. And as long as I manage the alphas correctly, I can get a progressive method out of it. Occam's razor. Okay, a solution to a statistical problem satisfies Occam's alpha razor if and only if whichever model is generating the data, the chance of conjecturing an answer more complex than the true one is less than alpha. So in a sense, like your method, if it makes mistakes, it errs on the side of simplicity. And the probability of making a mistake, erring on the side of complexity, conjecturing something more complex than the truth, whatever it is bounded. That's actually kind of a mouthful in English. But in symbols, it's quite simple. You know, a solution satisfies Occam's alpha razor if the truth in M is simpler than A, some answer, then the probability in M that your method says A is small. So if A is more complex than the true answer in M, then in M, the probability that you conjecture A is small for all sample sizes. N is arbitrary. So the probability that you ever say an answer more complex than the truth is low. That's all Occam's razor says. Okay, then last theorem. Every alpha progressive solution to a question must satisfy Occam's alpha razor. So satisfying Occam's razor, or is a necessary condition for this kind of almost monotonic convergence to the truth. Notice that I haven't put a prior over anything. The truth, whatever it is. So, for my case, a non-circular epistemic justification of Occam's razor in statistical science. Right, and the I guess the punchline is that a carefully calibrated Popperian methodology, where you do conjectures and refutations, but you carefully manage your outputs. You have a schedule of conjectures and refutations that's guided by simplicity, but you also have to carefully manage your outputs, can ensure that the degree of backsliding is arbitrarily low. Yes, and that's all for now. Thank you.